This is Raffaele Vitolo from the University of Salento. You see the title, and Raf, you are welcome to start. And well, please kindly switch off your microphones. So, Raf.
Okay. Thank you very much for your kind invitation, and it's always a pleasure to be at your seminar, even if it would be a much greater pleasure to be there in physical presence, something which I hope it will happen not in a not too distant future. So today I would like to speak about the latest results on WDVV equations and invariant bi-Hamiltonian formalism. This work was done together with a PhD student of Artur Sergeyev, whose name is Jakub Waszczyk. I will give you more precise references a bit later. Now I would like to make an introduction about why WDV equations are interesting and important object to study, and their meaning and their geometry. And then I will introduce the Hamiltonian formalism, which I will need in order to find Hamiltonian formalism for WDV equations, and discuss its geometric properties, which are probably the most interesting feature. I will start from first-order homogeneous Hamiltonian operators. They were introduced in 1983 by Dubrovin and Novikov. Well, they started from examples coming from hydrodynamics, and indeed, in such examples, you have quasi-linear systems of first-order PDEs, and it can be seen that such systems, in many simple cases, can be put in Hamiltonian form. Indeed, they started from multidimensional, I mean more than one space dimension cases. Here in this talk, we will only use one space variable. And so we will limit our consideration to quasi-linear systems of the form that you can see here in the first displayed formula. UIT equals Vij, which is a matrix of functions of u of the field variables times uj summed on j. You can have here as many field variables as you wish. Let us say n. If the system can be put in Hamiltonian form using a first-order homogeneous operator, then the system can be written in the form of an operator, first-order differential operator, P1ij, calculated on a vector function, the vector function which is the variational derivative of a Hamiltonian density, which is H1 here. The operators had the form, the first-order homogeneous operators have the form which is displayed framed in red, and this form shows you that the homogeneity property is in the x derivatives. I mean that each summand contains exactly one x derivative for a homogeneous operator of degree of homogeneity degree 1. The homogeneity degree coincides also with the order of the operator. So you have dx and then you have ux. This bit is of order 0, but it is of degree 1. An operator of this type is homogeneous only in the sense of x derivatives, but it is not homogeneous in the sense that it has the same number of derivatives in every sum, as you can see. The important fact about this operator is that it has geometric invariance properties. which make it a very interesting object to study, because also the quasi-linear first-order PDE systems are invariant in their form and the transformations of coordinates. Of course, the simplest transformation that preserves the form of this quasi-linear first-order system is a transformation of the field variables into themselves. But we will consider a larger class of transformations in this talk. Okay, so why these operators are so interesting? Well, for several reasons. The most important reason is that they happen in many cases in pairs, and as Dubrovin proved, plenty of operators of this type can be obtained using solutions of a partial differential equation system coming from topological field theory, which was first written down by Witten, Dijkgraaf, Verlinde. These Verlinde are twins. So every solution of these equations yields a pair, indeed, of Hamiltonian operators of the first order homogeneous. And this pair is a pair of compatible operators. This means that the PDE system is bi-Hamiltonian. Which PDE system? Indeed, when you start in this way from a solution of WDVV equation, for short, you obtain only a pair, but from the pair you can deduce the system of PDEs as the first flow, non-trivial flow of the hierarchy of that is generated by the bi-Hamiltonian pair using the Magri scheme. So the bi-Hamiltonian pair yields also the corresponding integrable system. And the bi-Hamiltonian pair also corresponds to a Frobenius manifold. We will not touch this topic, but every solution is a potential, every solution F of WDVV equations is a potential for a Frobenius manifold. So the interest in the solutions of WDVV equations is also in the fact that a solution of one of the WDVV equations when expanded into a series yields the dimension of certain moduli spaces, of course passing through generic points into a projective space, and this famous result by Maxim Kantsevich. So it is quite interesting for mathematicians to find solutions of WDVV equations and to study them. I do not know how much that is interesting for physicists, because, well, probably I can say that that is my ignorance, but what I see in journals of theoretical physics, on whose main subject is theoretical physics, I see that there is a certain degree of activity on WDVV equations. So it is still an interesting subject. Okay, so invariants of bi-Hamiltonian pairs with respect to the action of the Miura group have been introduced and studied, but this goes also outside the ends of this talk, so I will not speak about it. All right, so what is the geometry of the first order operators? Let us speak briefly about it. First order operators produce Poisson brackets, and these Poisson brackets are indeed Poisson brackets if and only if the operator is skew-adjoint and okay, it fulfills a certain differential constraint which is given by its Schouten bracket with itself, the vanishing of this bracket. And what happens for the class of operators that we considered is that if we go back to the form of the operator, which is here, this is a Hamiltonian operator if and only if Gij is symmetric. And then in the non-degenerate case, so determinant of Gij is different from 0, you can use the inverse of this matrix to lower one of the indices here in bijk. When you lower this index with a minus sign, this coefficient transform as the Christoffel symbol of a linear connection, and you can be, and the fact that the Hamiltonian, the operator is Hamiltonian, imply that well, it's equivalent to the fact that this connection is symmetric and flat. So it's the Levi-Civita connection of Gij, when in lower index you interpret it as a metric tensor. And there is also the additional condition of flatness. So you see there is a lot of geometry in these homogeneous operators, and since the metric G is flat, you can always find flat coordinates for the metric, and in those coordinates you reduce the operator to its canonical form, which is just a constant metric matrix times dx. Okay, now let us discuss the Witten-Digraph-Verlinde equations. I will follow the presentation given by Dubrovin in the Encyclopedia of Mathematics. The problem here is finding a function f of capital N independent variables in Rn. Okay, everything can be geometrized, but here I will follow the simplest presentation. So we are in Rn, and there are n independent variables, and there are several properties on these functions. First of all, the third order derivatives of the function, where one of the variables is always t1, which has a special meaning. This is a constant matrix, which is of course symmetric, and we require that it is non-degenerate. Then, since this is non-degenerate, you can use it to raise the index in the three-component tensor of the third-order derivatives of f. So you can raise one index through this constant matrix, and you get a family of indices of indexed numbers, functions, where you have one upper index and two lower indices. So this reminds the form of structure constants. And you can ask that these are indeed the structure constants of an associative algebra. This associative algebra is indeed a product on the tangent space of Rn, and you require that the product is associative. And these are exactly the WDVV equations, the so-called associativity equations. Then there is a further requirement of quasi-homogeneity, which is a requirement of physical nature. And the quasi-homogeneity is written here. And we will make use of this hypothesis. And but we can give results also in the case when this hypothesis is absent, and we will consider the associativity equation without this reduction. This is kind of reduction of the space of solution. So you can see below here in the last line what is the role played by the structure constant. And you can see that there is a special role of T1. The tangent vector to T1 is E1, and it is the unity of the algebra. Okay, so let us expand the equations of associativity, and we have this complicated formula here. So studying WDVV equations is important for the reasons that I told you. Each time you take a solution, you have an integrable hierarchy. And then there are relationships with Gromov-Witten invariants. And then there is a community which is active in quantum field theory, even if I do not know exactly what they are doing. Okay, now let me show you just, how to say, for kind of completeness of information, how to find a bi-Hamiltonian pair from a solution of WDVV equations. This is written in a big paper of Dubrovin that was published in Letters on Mathematical Physics. It appeared in archive very early, maybe 92, I don't remember. Okay, so consider a solution of WDVV equations, and then you have several homogeneity degrees here, D1, D2, and so on until the end. Then you can raise two indices using the constant matrix, the inverse of the constant matrix of third order derivatives where one of the variables is T1, this matrix which is defined here in point 1. We use the inverse 2 times instead of using it only 1 time. So we have a family of an indexed families of functions and with 2 upper indices and 1 lower index. And then what happens is that you can consider the operator P1, which is of the form eta I GDEq, which is clearly a homogeneous Hamiltonian operator in a trivial way, fulfills all the properties that are required to such operators. But then you have, in a non-trivial way, P2, which is an operator, a homogeneous operator, Dubrovin-Novikov of type, first order homogeneous. And the leading coefficient, which is the metric, the flat contravariant metric, is given exactly by this operation here.
Sorry, Raf, what is D?
Dk are the homogeneity.
The degree of homogeneity. Okay.
Yes. So you see, you can construct very easily bi-Hamiltonian pairs from every solution which is quasi-homogeneous, and this is very good. This means that you have plenty of integrable systems, and these two operators are compatible. This is also very important to observe. And this metric here is flat. This is also something not so evident, at least immediately evident. Okay, now I hope I gave you enough motivation to study WDVV, and now I would like to discuss the bi-Hamiltonian property of WDVV equations themselves. So, in a sense, you have the equations that determine integrable systems are integrable systems themselves. This was already proved by Dubrovin, to be honest, in 96, because he provided Lax pair, but he never thought about Hamiltonian structure for such equations, because the equations were written in, okay, you will see it in 2 seconds. They are not in the traditional form under which Hamiltonian formalism was developed. Okay, let us see what is the form of WDVV and how to transform them in a form which is more amenable of Hamiltonian investigations. So if df is different from 3, here I use a normalization where d1 is equal to 1. You can do it. You can rescale all the homogeneity degrees in this way. And then you require that df is different from 3. And then by linear transformations that preserve E1, these linear transformations of the space are, well, indeed, here there is also T1, because also T1 participates into such transformations. They preserve the direction tangent to T1. And by such transformations, it must be observed that such transformations are the invariant transformations of WDVV. You can easily prove that WDVV is invariant under these transformations. And okay, what happens is that you can transform the matrix eta from a generic matrix to this anti-diagonal identity matrix. I cannot find a better name than that to describe this matrix. So it has 1, 1, 1 on the anti-diagonal and 0 outside. And the form of the function f is completely specified in the part which contains T1 because of the requirement on third order derivatives. Plus, there is a kind of tail which is totally unknown, and it depends only on T2, Tn. And the actual WDVV equation is spelled out in terms of this unknown function f. So we shall not make confusion between capital F and small f. Small f is the unknown part into capital F. And then by linear, there is a special case df equals t. By linear transformations that preserve E1, which is again the tangent vector 2T1, we reduce the matrix eta to a matrix which is 0 everywhere. It has +1 on the anti-diagonal, and it has a non-vanishing constant in the eta 1 coefficient. And you can construct a capital function, capital F, which corresponds to this choice of eta. And again, the unknown part is a kind of tail, which depends only on the variables t2, tn. Okay, so we have two canonical forms. By the way, these two canonical forms can be reached when the weights di are distinct, the homogeneity weights. So this is a kind of restriction. I will tell you how to escape from this restriction, but a bit later. So we can consider the WDVV in the case n equals 3, and we have two equations because we have two normal forms of eta. So we have the first equation, which was widely studied, and a second equation, which was not so widely studied, I would say. Sorry, here there is how to say, not a misprint, but this mu corresponds to this constant c here. Sorry, this is my fault. So mu, this should be read mu instead of should be read mu instead of c. Mu is here. So you have indeed a family of equations with one parameter. And what happens to these equations? Now we introduce a trick, which was a construction. It's not a trick, it's a construction by Alek Mohov in 95. He introduced three new coordinates, which are A, B, and C, with the feature that each of them contains at least one x derivative. Here in this language, in order to simplify things, x is T2 and t is T3. So these are the remaining variables. We are in the case of capital N equals 3. So you see that T2 is x and T3 is t in the unknown tail of the WDVV potential F, capital F. So when you introduce these new coordinates, then you have compatibility conditions, because you see that AT should be equal to BX, because, okay, this is just a theorem about commutativity of derivatives. But this is also conservation law. And then you have another conservation law, because you have BT equals CX. And then finally you have CT equals, okay, you need the equation here, because you would have F 3 times derivative with respect to t and derivative with respect to x, but then you replace f 3 times derivative with respect to t with the equation, which is here, and this is just the letter b to the square, and this is letter a and letter c. So b square minus ac, and exactly the same mechanism holds for the other equation, where you produce this system of conservation laws. Okay, the fact that this system is bi-Hamiltonian was already observed by these four people, Ferpontov, Galvon, Moch, Nutku in 98. And they observed that it is bi-Hamiltonian by a third order and the first order Hamiltonian operator of Dubrovin-Novikov type. So what about the system on the right? Well, about the system, nobody cares, or nobody knew. So we have entirely new results about this system, but we will see them a bit later. Now let us go ahead and tell a little bit more about higher order homogeneous operators, because I say that the WDVV system has a third order homogeneous operator. What are higher order homogeneous operators? Okay, you just consider summands in the operators where each block has 2, for example, x derivatives, or 3 x derivatives. So this is the case of second order operators, as you can see here, are 2 or are 3 third order homogeneous operators. You can see that the structure is very complicated. These are very difficult objects to deal with, in principle. Okay. Let us see what are the operators for the eta 1 associativity equation in its simplest, which is the simplest possible instance of WDVV equation. Let me remind you that the first non-trivial case with respect to the dimension is capital M equals 3. And this is exactly the case when you have only one scalar equation. Okay, this is the way how the equation is rewritten as a hydrodynamic type form in a hydrodynamic type system or a quasi-linear system of the first order. So the operators are written here. They are P1 and P3. You can see that P1 is first order homogeneous, and P3 is again first order. It's third order, but again homogeneous. P1 and P3 are completely determined by the leading coefficients. It is about the statement about P1 is obvious. It's what I told you before. It's an old result by Dubrovin and Novikov. The statement about G3 is relatively new. It was discovered by Pavlov and myself a few years ago. Let us say something more about third order operators. I know that many of you already heard these things sometimes here in the seminar from me or from Maxime or from somebody else, but I will rehearse the very essential things. So all third order homogeneous Hamiltonian operators can be rewritten in a canonical form, which is here. And in this form, the operator is factorized. It has a first order dx before and after a first order operator, which is much more simple than the full size third order homogeneous operator. So you have much less coefficients than the most general case, and such coefficients are related in such a way that C3, the block C3, is completely determined by G3. And the formula for the determination is here. You see that C3, you have to rewrite C3 in lower indices through the formula which is on the bottom of the page. And then you have two further properties. One property which says that G is a Monge metric Monge metric means that it determines a certain algebraic variety, a projective variety, which is very interesting because it means that you have projective geometry in these WDVV equations. And then you have a further constraint. This is a nonlinear constraint, which is essentially a nonlinear equation on G, on the coefficients of G, because C3 can be completely determined by the first order derivatives of G. Okay, and what about projective invariance? It was proved some years ago, that certain specific reciprocal transformations preserve the canonical form of the third order operator. And these are transformations where the dependent variables undergo projective transformation, while the independent variables undergo a non-local transformation, which is of the following form. Delta here is a linear form, and it is the denominator of the projective transformation. And it is also interesting to observe that the leading coefficient of the operator is transformed, as you can see here. Okay, then there is also classification result on third order operators. So in the case n equals 1, we have only one case, d^3, which happens as a summand in, for example, the second Hamiltonian operator for the KdV equation or the Kamasa-Holm equation. So in the case n equals 2, there is also, well, a simple operator in the projective classification. In the affine classification, there are three normal forms. The simple operator is just this anti-diagonal matrix multiplied by d^3. And in the cases n equals 3, n equals 4, the situation is more complicated, and there is an increasing amount of projective geometry. The case n greater than or equals to 5 is not, how to say, the classification is not possible. There are so many normal forms that it just makes no sense. Okay, now how to relate third-order operators and systems of conservation laws. This is paramount for us. It is of paramount importance because we have systems of conservation laws and we want to find third-order operators. For first-order operators, there are conditions of compatibility between systems of conservation laws and first-order operators, and they were found by Sergei Tsaryov in 1985, maybe. Well, but what is interesting is also that to each system of conservation laws, one can associate a certain algebraic variety. This is an algebraic variety in Pn+1, which is it is called the congruence of lines. It is an n-parameter family of lines into a projective space of dimension n+1. This is interesting because, as I told you, third-order operators have a projective meaning. The systems of conservation laws have a projective geometric meaning. So we start to see the emergence of lots of projective geometry. Okay, there is a method introduced by Kersten, Krasichuk, and Vergovietsky in 2004. This method allows to characterize which Hamiltonian operator could be, which operator could be the Hamiltonian operator of a certain system of PDEs. And this method is very general. Here, in this circumstance, we applied it to the very restricted case of third-order operator, homogeneous, in canonical form, and a system of conservation laws. And what we obtained is a system of conditions which is very easy to compute with. So each time you have a system of conservation laws, if you run this computation, you can find if the system admits a third-order operator in a few seconds with any computer. This system also allows to connect the WDVV systems, the systems obtained by WDVV, in WDVV case, with third-order operators. I mean that if you go back to our example here, for example, you use the equations that I showed you before that connect third-order operators and such systems, and immediately find third-order operators in seconds, literally. This is absolutely non-trivial because usually finding a Hamiltonian operator for PDEs is quite painful because you don't have a clue about the ansatz for the operator, the ansatz, and if you make a general ansatz, the computer starts computing. While in this case, since you make very specific assumptions, you solve everything quite quickly. Now, of course, you have to have good candidates, and WDVV proved to be perfect candidates because you could find such operators very easily, not entirely by chance indeed. So we proved that WDVV system, when I say WDVV systems, I mean exactly systems of conservation laws like this one here, which is obtained after WDVV equation with the technique introduced by Alec Mohoff many years ago. So from a WDVV equation, you introduce new letters. These new letters have compatibility conditions. You express the conditions through the WDVV equation, then you have a system of first-order conservation laws, which is also a quasi-linear system of first-order PDEs. Then we were able to prove that in low dimensions, so to be more specific, in the cases n=3, n=4, n=5, in both canonical forms by Dubrovin, eta1 and eta2 that I showed you for WDVV equations, when you put them into the form of quasi-linear first-order systems of PDEs, they have a third-order homogeneous Hamiltonian operator in canonical form. In the case n=3, we were also been able to prove that also the canonical form eta 2 is bi-Hamiltonian. So it also admits a first order homogeneous Hamiltonian operator. The point is that this operator is non-local, so it's not so easy to find it. And the other new result is that this operator is compatible with the operator, with the third order operator that we find on such systems. And this was also some non-trivial calculation which we have been able to do because we developed specific software for these calculations. Indeed, we developed a software which is able to compute the Schouten bracket of operators which belong to the so-called weakly non-local operators family, which was introduced by Maltsev and Novikov, I think 2001, 2, like this.
Sorry, may I ask a question?
Of course.
You say the operator is non-local of Fierapont-of type.
Yes.
Will you explain what means non-local of Fierapont-of type?
Of course, in a very short while, maybe in the
Okay.
next slide. Okay, so in the case n equals 3, we also proved that the bi-Hamiltonian pair is invariant with respect to the invariance group of the WDVV equations. And this means that whenever you find the bi-Hamiltonian formalism on one canonical representative, then it goes along the orbit. And this means that every WDVV equations can be represented in the form of hydrodynamic type system, which is bi-Hamiltonian. In the case n equals 3, which is quite restrictive, but still it is something. Okay, so no, it is not in this slide, but it will come in very few slides. It's okay. Okay, so WDVV systems, new results. There are also new results on the projective geometric properties of the WDVV systems. And it follows from the equations that I discussed here, these equations coming from the method by Kersten, Krasichin, Verkowiecki. From these equations, it follows that every WDVV system defines a multi-parameter family of first-order systems of conservation laws. Okay, this is known, but not defines, but every, no, this is slightly wrong, sorry. What I wanted to say is that every WDVV system has a third-order operator in canonical form. So third-order homogeneous operator in canonical form. Oh, and then what happens is also that there are additional properties on the WDVV system if you regard it as a projective geometric variety according with the construction by Agafonov and Fierapont, this construction which I shown here. So if you consider the projective geometry of the systems, you have the additional properties that the congruence is linear. So this variety is, this algebraic variety is the intersection of the Grassmannian in a certain projective space with linear subspaces.
Sorry,
yes.
may I ask something?
Oh, yes.
You say every WDVV system.
Yes.
Wait, so I remember you had two canonical forms for your WDVV equation. Do you mean this system or something else?
This means that in both canonical forms you have this. So you have that a third order operator. And since these two canonical forms fill the whole space, you can make a general statement.
So
coming from the, yes?
So when you say every WDVV system, you are speaking about two systems.
I am speaking about two systems, their orbits, and this means every possible WDVV equation, because you will have that these two orbits give you all possible values of theta. Let us come back to here to the so we have these two forms of theta. We are still in the case when we have weights that are distinct. So you have two canonical forms of eta, and hence the WDVV equations are two equations, two possible equations. These two possible equations are the equations that I showed you here. We are in the case n equals 3, in the simplest case.
Right.
So you have two equations, and these two equations can be transformed into two systems, and these two systems have a third-order operator, and this third-order operator is homogeneous of the canonical form. But then these two systems fill the whole space, provided the hypothesis that I told you, so homogeneity weights are distinct, are fulfilled.
Okay.
And then all right, so the congruence is linear. Okay, suppose you don't care about this projective geometric feature, but then this projective geometric feature yields the fact that the system are always linearly degenerate. So each time a system has a third order homogeneous operator, it is linearly degenerate and non-diagonalizable. Another property is that the fluxes of the conservation laws are rational functions of a certain degree. And the final property is that the system of the hydrodynamic type system also admit non-local Hamiltonian momentum and Casini's with respect to third-order operators. This happens every time that you are able to prove that the hydrodynamic type system has a third-order operator. Since our WDVV systems have a third-order operator, they all fulfill these properties. Okay, and then let us see the form of the third-order operators. So this is the metric of the third-order operator in the case eta 2, because in the case eta 1 it was already known. In the case n equals 3. So we have a third-order operator which is of a form which is not extremely complicated. Okay, but then in these coordinates, of course. And then the first-order operator. Now, so again, this is a first-order operator of a Rapoport type. Well, first-order non-local operators were probably first found, well, for KDVE. After applying the recursion operator to the third-order operator of the KDVE, you have a fifth-order non-local operator. It is of weakly non-local type. And then I think that Sokolov found an operator, I don't remember for which equation, probably non-linear Schrödinger. It was ux d minus 1 ux. So quite simple.
Possibly Krichyver-Novikov equation.
It is probably true, yes.
Which is a scalar equation of order 3, very similar to KDV,
yes,
but it is related to an elliptic curve.
You are right, because of course NLS is two components, so I was wrong. And then Ferapont studied non-local operators of more general type. The type was, well, you had a constant times ujx d minus 1 uix, like the last bit of this operator. You see, the last summon. But then Ferapont went ahead and proved that there are more general non-local operators in this than these. And they have very beautiful geometry. They are connected to the geometry of hypersurfaces in higher dimensional space. Okay, but in this particular case, we have a specific form. It's not a generic bond of type. It is a specific form, because you see that these blocks here, you have a vector before dx minus 1 and the vector after dx minus 1. In some cases, you have just velocities, but in some other cases, you have the velocity matrix of the system, the hydrodynamic type system, multiplied by velocities. So it's more involved, much more involved. But it can be determined only by three constants, alpha, beta, and gamma. And what happens is that eta 2 has exactly one first-order operator, which is written in this form. And okay, delta is quite complicated. So as you see, it is really non-trivial computation. An interesting feature is that in the denominator you find the determinant of the leading term of the third order operator. So this cannot be a coincidence, but unfortunately we do not have a projective geometric interpretation of this operator, while there is a beautiful differential geometric interpretation of the operator given by Ferrapont many years ago. Okay, so we can go ahead and speak a little bit about invariance. So we have invariance property. The WDV equations are invariant under linear transformations that preserve the direction of d in dt1. So they have the following form, and you have the fact that okay, determinant of p alpha beta is different from 0. This is just a translation. But then the interesting point is that you have a non-zero element only in the first entry of the first column, and all the rest of the first column is 0. Okay, and then we have a theorem, again in our paper together with Jakub Vasicek. We published it in the Journal of High Energy Physics. Okay, so when n equals 3 and you have a WDV system in first order form, then it is always bi-Hamiltonian with respect to a pair of compatible Hamiltonian operators. One is non-local first order in general. In some cases it is local, and another is a local third order operator. And it must be said that the invariance transformation does not change the form of the bi-Hamiltonian pair. So what is non-local remains non-local, what is local remains local. And what is third order operator in canonical form remains a third order operator in canonical form. And this is not so trivial to prove. Well, it was proved in a paper by Jennifer Ferrapont, Maxime Pavlov, and me some years ago. I think 5 years ago. Okay, so invariance in detail, how to construct the matrix. The matrix of the change of coordinates, the most general matrix is this, P is equal to this, and this is 1, so it's not just a non-vanishing element, it's exactly 1. So you can factorize this matrix in this way, and when you factorize this matrix in this way, then you can refactorize T1 into this transformation, which is a transformation that affects only independent variables in principle, but of course then it has reflections on the dependent variables either. The effect on independent variable is that of an holonomic reciprocal transformation. Holonomic reciprocal transformation means that you can always integrate it to a transformation of the independent variables, because indeed this is a linear transformation of the independent variables. This is easy, but what it is difficult is proving that the third order operator is invariant under this type of transformations. This R2 is just reciprocal, or R1. These are just induced reciprocal projective transformations of the full set of variables, and as we have shown, this leaves the canonical form of the operator invariant. And this E is just inversion of the two independent variables, and this we also proved that the inversion of T and X preserves the canonical form of the third order operator, which is non-trivial. So altogether, these transformations do not affect the form of the bi-Hamiltonian pair, and this is the invariance result. Then what happens is that there is a very interesting paper, which, by the way, inspired this research, I shall say, by Mokhov and Pavlenko. They dropped the requirement on quasi-homogeneity on the solutions of WDVV, so there is no such a reduction. And they used only transformations of type T1, so this type here. So transformations of the T2 and T3 in language of WDVV equation, or X and T in the language of hydrodynamic type systems. And then what happens is that they found 4 canonical forms. And in all these four canonical forms, we found a bi-Hamiltonian pair of the type that we specified. But Mokhov and Pavlenko already found that eta1 is the only canonical form that has a first order local operator. They found the operator for the canonical form eta1. But then what we found is, okay, third order operator for this, and it is quite easy, but also for eta3, eta2, and eta4. Third order operator. Plus, we found that eta3, eta2, and eta4 have a non-local operator first order of a point of type. More specifically, the type is exactly what I showed you before. So this type here, equation number 8. So 3 constants and the tail, which is determined by a certain combination. The non-local part is determined by a certain combination of the vector of first order derivatives of field variables and the matrix of velocities multiplied by the vector of first order derivatives. So the right hand side of the hydrodynamic type system. In a language that was introduced by Joseph Krasicik and Alek Vergovietsky, you need 2 non-local variables to describe this operator, but it can be done perfectly with their formalism. Okay, and then another news is that all these pairs of operators are compatible, and this is proved thanks to software which is able to do the computation and an algorithm that we found for computing compatibility of operator or computing square and brackets of non-local operators of weakly non-local type. Okay, I just would like to show you a specific example to show you how much geometry is in here. This is a very special type of choice of eta, which is not in the canonical forms, but it was explicitly considered by Dubrovin in his paper Geometry of 2D Quantum Field Theory. And Gianni Ferraponto found that found several interesting connections with the central affine geometry. Namely, this equation, this WDVV equation, is also the equation of flat central affine matrix for surfaces in R3. Well, there is a book, which I think it was never translated in English, on affine geometry, on affine differential geometry. It is the geometry of GL something, GLN. Okay, and then for this equation, we found, okay, in hydrodynamic type form as a system of conservation laws, we found a third order Hamiltonian operator and a first order non-local operator, which has a very peculiar structure because its constants are alpha 0, gamma 0, and beta equals to -1. And this means that the operator is localizable by reciprocal transformation. Indeed, if you come back here, okay, so when you have alpha 0 and gamma 0, the operator which is here can be seen to be the image of a reciprocal transformation by a reciprocal transformation, general reciprocal transformation of a local operator. But this reciprocal transformation is not an equivalence transformation of WDVV equations. So it's a more general and difficult transformation. Okay, okay, we can speak a little bit on the higher dimensional cases, which are much more complicated, and we have weaker results, not very strong. So in the case eta1, when n equals 4, you have 4 of a determinate equations which are quadratic in one unknown. So the system is over-determinate and nonlinear. It is a real system. I mean, here you cannot reduce everything to just one equation. You have 5 equations. And then this is again a trick which I read in a paper by Ferraponto and Moho. And the trick is that you introduce new variables. Always variables correspond to derivatives of x which contain at least one x derivative. And here are 6 in this case. And then you have several compatibility conditions. If you freeze another independent variable, you just consider, for example, y. And then you have, if you consider y, you have one system of conservation laws. If you freeze the other independent variable, you have another hydrodynamic type system. And what you can prove is that these two systems are commuting flows. What we proved with Maxime some years ago is that both systems admit the same third order operator in canonical form. And here, this is the matrix of the leading coefficient with lower indices. It was extremely painful to find this operator until we realized that everything would be easier if one would apply the characterization by Joseph Krasicki, Khalil Verbowiecki, and Paul Kersten. And when we had those equations at hand, it was just a matter of seconds. And then we found this operator. A first order operator, local, was already known, and then it was natural to check compatibility, and they're compatible. Okay, but
sorry,
then,
may I ask? So do
yes.
Do I understand correctly that the third order operator is non-local?
No, it is local.
You say that the first order operator here is local, but
yes.
you do not say on the slide it is not written local about the third order operator.
In this talk, I always spoke about third order local operators. I never spoke about non-local operators until the very end. In the very end, I will make a comment on non-local third order.
So all third order operators are local.
Local in this setting, in WDVV.
Yeah, okay.
Okay, so in the case n equals 3, the compatibility is a very hard computation. And it was checked with this new algorithm that we developed together with Matteo Casati and Paolo Lorenzoni. And we also wrote packages for the computation, and the paper should appear soon, and it is already in archive and in our website GDEq.org. So in the cases n equals 4, n equals 5, when for every eta, we found third order local homogeneous operators in canonical form. So this allows us to conjecture that they exist in every dimension. First order operators, unfortunately, at the moment, they are known only in the case n equals 4 and eta 1. In the case n equals 4 and eta 2, and in all cases n equals 5, they are not known for the moment. Some comments. So WDV equations have third order Hamiltonian operators, and these correspond to certain algebraic varieties, which are called the quadratic line complexes. And then we have quasi-linear systems of PDEs, and these are other projective varieties in another projective space. The quadratic line complex is in a space which it is the space of lines of Pn, while the linear line congruence, which corresponds to every quasi-linear system of PDEs, is in the projective space Pn+1. So in generally speaking, the dimensions are different, and this is not so easy to figure out how to find one thing from the other, but there should be a relation, because you can always find a quasi-linear system of PDEs when you have a third order operator, and conversely, the other way around, when you have a quasi-linear system of PDE of WDVV type, then you find the third order Hamiltonian operator. So there should be a way to pass from one variety to another. We still do not know it. And then the compatible first order operators, this is a mystery, the projective geometric meaning. I would bet, I don't know, okay, I would bet on the fact that this has a projective geometric meaning, but at the moment I have no answer to this question. The point is that I think, I'm almost sure, that everything will be more clear if we will be able to understand completely all these geometric structures in terms of the original coordinates. There was already a paper by Kirsten Krasicki and myself, but it is still quite difficult to connect the objects which are in that paper with the objects that are in this current research, because it's not so easy to make a change of coordinates. And then I would like also to add the fact that if you generalize WDVV, there are equations of F-manifolds, the so-called F-manifolds. And we proved together with Maxime Pavlov that in the simplest case, there is a non-local homogeneous third-order Hamiltonian operator. So these operators should be a property that should be readable in terms of the original coordinate system. There should be a geometric property of WDVV which says, okay, there is a certain algebraic variety or more algebraic varieties that are attached to these equations, and you can find them in this and this way. But we still do not have results that I can show you. We have some conjectural thinking at the moment. Okay, all symbolic computations were done with reduce, which I like so much. And I was introduced to reduce by Paul Kersten, and then I had cooperation with Arthur Norman, who is one of the main developers of reduce and who helped me to understand it and to write efficient packages. And together with Joseph and Alec, we wrote a book on the symbolic computations of many different quantities related with integrable systems, symmetries, conservation laws, Hamiltonian operators, Gaussian operators, symplectic operators, and so on. If you are interested, you can ask us in private. Okay, thank you very much. I am again very happy that the seminar restarted, and I hope that sooner or later we will meet all in person and do a big dinner, big drinking, and big party, because this how to say abstract way of doing talks is now okay. It is lasting since almost 2 years, and it's too much in my opinion. Okay, thank you very much.
Okay, Raf, thanks a lot. Quite interesting. Questions, remarks, comments?
Can I ask a question?
Yes, sure.
Well, Raf, can you go to the previous slide, to your last slide?
This or?
Right. No, the very, well, yeah, here, symbolic computations.
Mm-hmm.
I know that you have written a lot of packages for reduce, and it probably works. Well, it definitely works. But is it possible to translate your reduce packages to either Wolfram Mathematica or Maple? Because Wolfram Mathematica and Maple are in principle much more popular than reduce.
Oh yes, of course.
Many more people have knowledge of Mathematica and Maple than reduce. Right?
I agree. And indeed, in the last, since I wrote a paper in collaboration with Casati, Lorenzoni, and Valeri, they had packages in Maple and in Mathematica. We have new packages in Maple and in Mathematica for the computation of scope and bracket. So if you contact me in private, I will give you the latest versions, which are under review in a journal. So I still didn't make them public, but I want to do it soon.
But latest version of what?
Sorry?
You can give me the latest versions of packages.
So one Maple package which can compute scope and bracket with local and non-local, weakly non-local operators, and the same thing for Mathematica.
So if available also for Mathematica. Okay.
Yeah.
Okay, thank you very much.
More questions? Okay, Raf, thanks a lot again. So we meet in a week, the same time, again in Zoom. Everyone is cordially invited. Thanks for participating, and
Thank you very
goodbye.
much.
Goodbye.
Bye-bye.